Okay, so let's start today. We'll look at the second derivative test. So the whole idea begins with Rolle's theorem. Remember, Rolle's theorem says that if a function has derivatives and if its values at two endpoints is 0, so somewhere in between there is a horizontal tangent. The derivative is 0 somewhere in between. So lots of things were proved by this. Mean value theorem followed from this. So we'll now have a slightly generalized version of mean value theorem, which is going to be a preparation for what we'll do at the end of the semester for Taylor series. So here, let f be a nice person, differentiable, etc. So we claim that the value of f at x is going to be slightly different than the value at x sub 0. So the mean value theorem says that the error factor here is given by the first derivative. So we'll carry it a little bit more. We'll say that we can approximate this by the first derivative, x minus x sub 0. Now here is the error. This is one variable. Okay, so remember. So this is the equation of the tangent line, and the error is given precisely by this thing. Okay, so for some unknown c between x and x sub 0. Okay, so there is a price paid for this. We know exactly what the error is, except that we don't know how to calculate it, because it will be calculated at some point. The power of the claim is that there exists a point where the function itself tells us what the error is. Okay. So if this c was here, remember it was mean value theorem. Okay, so this is our claim. So why does it hold? Okay, so we'll prove this again with two applications of Rolle's theorem. So for this, we do a small trick. So first of all, fix x and x sub 0. Okay, so we are trying to express the value of f at here, if the values of f at this point. So we fix them and we see if this really holds. So when you fix them, and of course when we fix them, we make sure that they are different. Otherwise, you see, there's nothing to prove. Now set a constant, set k to be equal to, okay, I'll write it like this. So this whole thing, this minus this part, okay, so f of x minus f of x sub 0 minus f prime x sub 0 x minus x sub 0, okay. So I want to divide it by this thing, x minus x sub 0 square. Okay, so observe that if I put it here, okay, so, well, here, so this is taking the place of this thing. I'm trying to recover the value of k. Okay, and define a new function. Say phi of t, okay, so I write phi so that it looks scientific. Phi of t is this obvious thing, f of t minus this part again, f of x sub 0 minus f prime x sub 0, except that instead of x I put t minus x sub 0 minus k times t minus x sub 0 square. Okay, so this function is defined wherever f is defined, because the other parts, this is a polynomial, this is a polynomial, they are defined everywhere. Okay, now check that. Phi of x sub 0 is 0, okay? If we put x sub 0 for t, this and this cancels. These are 0, so you get 0. Also, check that if I put x for t, this is 0. That's precisely why I chose k like this. Okay, so the whole idea, the whole trick here is put an arbitrary constant here, okay, and whatever that constant is, when you put t equals x sub 0, you get 0. Now, choose that constant so that this is also going to be 0 when you put t equals x, okay? So we have this. Now, by Rolle's theorem, somewhere in between, the derivative of this is 0, okay? Phi prime of c, okay, let's see c prime because I'll need c later on, is equal to 0 for some c prime between t and x sub 0 and x, okay? So between these things, between x and x sub 0, okay? So let's write phi prime and see what it is. Phi prime t, on the other hand, is equal to f prime t. This is constant, okay? So this is minus, this is just one, linear, minus f prime x sub 0, okay? So I got rid of this. And here this is constant, and I have this. So minus 2k t minus x sub 0. Okay, so let's let's check. Now, from here, clearly we have check also that phi prime x sub 0 is 0. Okay, so because this and this cancel, this is 0. We also have this. Okay. We also had phi prime c prime equals 0. So by Rolle's theorem, there is a point C between x and, so by Rolle's theorem, there is a C between x sub 0 and c prime, such that phi, the derivative of this, at c is equal to 0. Okay, so this doesn't make much sense because we don't know where c prime is. So this is not going to restrict our c. All we know about c is it is between x and x sub 0. Okay, because this point is between x and x sub 0. This is the picture. Suppose that x sub 0 is smaller than x. Okay, I'm not putting arrows. Maybe this part is larger. C prime is somewhere here, and C is somewhere here. Since I don't know exactly where this is, if I'm going to describe this, the only thing I can say is it is between x and x sub 0. Okay, so this is x sub 0 and x. Okay. Okay, so let's write second derivative of this. Phi t is equal to f double prime t. This is constant, it goes, and here I have minus 2k. Okay? So I know that this is equal to 0 when, so taking this over here, I have c minus 2k equals 0. So k is equal to f double prime c over 2. Okay? So now you put this here. Okay, so we also have, okay, so let me put things like this, and let's say this is big star. Okay, putting this into star, we get the claim star star. Okay, so so you see that it's not magic. This works, and later on we will keep doing this, because you see, if I can do it with 2, why can't I do it with 3? Yes, you can do it with 3. Now here you put x sub 0 And for the third derivative, you can put c. Okay, but the denominator now will be 3 factorial because you see, how did I obtain this 2? I started with this. I took its derivative. 2 came here. Then I took its derivative once more, and I obtained this. So this is actually 2 factorial. Okay, so I can go like this up to 35, and then the last term will be 35, 1 over 35 factorial. So why stop at 35? We'll go up to infinity. Okay, so that's what we will do when we come to sequences and series. Okay, but you see, that's why we give a name to such very simple results. By Rolle's theorem, everything rolls. Okay, so now we'll use this. You see, this is for one variable case. Now we'll use this to understand minima and maxima of functions of several variables. So let me start with the 2 variable case. Actually, we can use this such similar ideas for higher number of variables, but the calculations get messy. So just to get the idea and to be able to solve a few problems by hand, we will do this for 2 variables mostly. Okay, so now consider a function of 2 variables. Okay, so there is a point x sub 0, y sub 0. So this corresponds to our x sub 0 in the previous case. We move to a point x and y, but we want to, since in one-dimensional case, I didn't mind writing this only x, because the difference I wrote x minus x sub 0, but now there are 2 differences. Just to make notations easy, I'll write this as x sub 0 plus some increment, y sub 0 plus some other increment. And remember, last time I said x different than x sub 0. Last time is just 2 minutes ago. So here I want, if I want this point to be different than this point, all I want is that this point is, this increment is different than the trivial increment. So one of them can be 0, but both of them will not be allowed to be 0. I consider this line. Okay, I will restrict this function to this line. And in particular, I'll be interested in what happens in between. So a typical point here is of the form x sub 0 plus you move a little bit in this direction, y sub 0 plus you move a little bit in this direction. Okay, so that's a typical point. Now what I want to do is I want to restrict this function here, calculate the value here and here, look at the difference. If no matter which hk I choose, the difference between the 2, this minus this, is positive, it means that this is a local minimum. Okay, because this cannot be, in that case, it says that this cannot be larger than the values around this point, so it will be a local minimum. If always, no matter which h and k you choose, the value of f here minus the value of here is negative, it means that this guy is large. So it's a local maximum. Okay, so we are trying to get this region, this result. And this result will follow from that, because when I restrict this function here, it's a function of t. I'll write this result, this claim here, and see what happens. Okay, so let me do that. Restrict f x y to the above line. Then we get a function of t. Okay, so f of t. So let's say this defines a new function, f of t. I'll evaluate this at this point, f of x sub 0 plus th, y sub 0 plus tk. Okay. Here I'm interested only in between here, because you see what happens if I move here. If I move here, I'll change the signs of h and k. Okay, it will be minus h. Whatever this direction is, I'll put minus h minus k here, and I'll consider the function here. Since in the back of my mind I'm allowing h and k change, arbitrarily, provided that both of them will not be 0. I'm covering everything around this center point. Okay? So I say it is enough for me to consider t only between 0 and 1. Okay? Now observe that f of 0 is this point, f of x sub 0, y sub 0, and f of 1 is this point, f of x, y. Okay. Now I'll try to write f of x, y in terms of this, just like we did in the previous claim. Okay. And then we'll stare at it and try to see if we can say a little bit more. Okay, so previous result, so previous claim applied to this. Now I'll do this for this. So the value at f1 is equal to the value at f0. Okay, so plus the derivative of this at 0 times 1 minus 0. Okay, so you see how nice the things work. Plus the derivative, the second derivative at an unknown point in between, divided by 2 factorial times this minus this squared, 1 squared, so it is here. So this is the result for some c, and Rolle's theorem says that this is definitely going to be an interior point, so let's stick to that. Okay, so now I take this and write it here. Okay, so the nice thing here will be I'll use the chain rule here, stick these numbers in and see what comes out. Okay. So I'll have okay, so we have now using the definition of f, I have on this side I have fxy. Okay. On this side f0 is, you see, just this thing, f x sub 0, y sub 0, plus, now I'll take the derivative and evaluate that t equals 0. That means I'll evaluate the derivative at x sub 0, y sub 0. So let's take the derivative of this. By chain rule, I take the derivative of this with respect to x times the derivative of what I see in place of x with respect to t. So it will just give me h. Okay? So this is fx x sub 0, y sub 0 times h plus fy x sub 0, y sub 0, k plus. Okay, things are looking good so far because you see I'll apply this at a critical point because my local minimums and local maximums will appear among critical points. At the critical points, these will be 0. Okay, so I will not have these terms when I say let's start with the critical point. So what we will have is the second derivative here. So the second derivative is when you first take the first derivative of this and then you take its derivative once more. Okay, so I'll write it for you. But then I will not evaluate it at t equals 0, but I'll evaluate at t equals c. So inside I'll have these things. Okay, so let me write it here because it's a bit long. So this whole thing. So let me just write it because you see, now I have this, but inside here I have x sub 0 plus th. So I'll take the derivative of this with respect to x, okay? And then evaluate the inside at t equals c. I'll have x sub 0 plus ch, y sub 0 plus ck times h, and I have another h here. Okay, so maybe I put that here. So I'll have h squared plus I'll have a derivative xy and derivative yx. So let's assume that this is a nice function with continuous second derivatives. Then these mixed partials will be equal. So I'll have two of them, 2fxy x sub 0 plus ch, y sub 0 plus ck, and I have h coming from here, k coming from here. I'll multiply them. Okay, so here I take the derivative with respect to x, it will be hk. Here I take the derivative with respect to y, I'll have kh, so this is hk, plus fy y x sub 0 plus ch, y sub 0 plus ck, k square. Okay, so this is what we have. At a critical point, these will be 0. Okay, so if x sub 0, y sub 0 is a critical point, these will be 0. Okay, so that's the definition of critical point. So you see we are interested in the sign of this minus this. At a nearby point, if h and k is very small, x, y is very close to this. So that's how you check if f of x sub 0, y sub 0 is local minimum or maximum. You check the value of this. Okay, so let's give a name to this. Okay. Call this Q evaluated at C, okay, or some other thing, remainder at C, or for some reason, right now I call it Q, okay. Of course, this depends on H and K. This depends on H and K, but we keep it in mind, okay? Because we want to be able to say something about QC for all possible H and K. Okay? If we can do that, then we can tell whether this point is local minimum or maximum. So what happens is this. We have fxy minus fx sub 0, y sub 0 is equal to QC. Now, if QC is always positive for all possible H and K, then this number is always larger than this. So this is a local minimum. Okay, very nice. But you see, we are trying to say something about this for all possible HK, but we know that if you just change H and K, C will change. So this side is impossible to calculate. Okay? But what is possible to calculate is if instead of C you put 0, then we suddenly have something we know here. Okay? Everything we know about f evaluated at a given point, the point is fixed. Okay? So let me make a remark of this. If QC is positive for all possible HK, but of course I don't want 0, 0, then f x sub 0, y sub 0 is a local minimum value for f. Okay? Of course, if it is negative, then I can say something. If it changes sign, then it's going to be a saddle point. Those observations are clear. What is challenging at this point is how can I tell the sign of this? I cannot tell the sign of this, but since everything is continuous, you see, I need everything to be continuous. So in the beginning, I'll put conditions like this. When I start this claim of the second derivative test, I say f is a nice function. It has continuous partial derivatives, so I was able to write this. The partial derivatives are all continuous, so I can say that the value at this point is close to the value at nearby points. In particular, if Q0 is positive, okay, then by choosing H and K small, I can make all possible QCs positive. Okay, because you see, if this is the 0 level, if a function is continuous and it is positive here, if you move a little bit around, it is still positive. It can go down to 0 very fast, but it doesn't go to 0 instantly. Then it would not be continuous. Okay, the graph is not broken. Okay, so we make use of that condition that we studied in the first weeks of calculus. Okay? Since everything is continuous, I have this. If Q0 is positive, then QC is positive for small hk. Okay, so you see that the important thing here is the direction. Hk determines me the line. So there is no point in taking h and k very large. If you take h and k very large, I can divide both h and k by 1 million or 10 million, and I can make it small, and still I'm working on the same line. You see, the whole idea is restricting f to that line. Okay? So the size of h and k doesn't matter, only the ratio between them is important. So this part is no problem. I can always make h and k small by respecting the ratio between them. I can start with nice functions. We'll be working with polynomials, trigonometric functions, etc. Their derivatives are all continuous. So this condition, this everything condition is no problem. Okay, so then this is true. Okay, I can calculate Q0 because putting C equals 0 here, I get an expression which I can calculate. F is given, x sub 0, y sub 0 is given. So the question is this: how can I know that this expression, when I put C equals 0, is going to give me positive no matter which hk I choose? So let me start from there. Okay, so let me write that now. Okay, so let me erase this one. Okay, so here Q0 is the following. Q0 is fxx at x sub 0, y sub 0, h squared plus 2 fxy x sub 0, y sub 0, h k plus fyy x sub 0, y sub 0, k squared. Okay. So these are numbers. Okay. So these things are numbers. See, this is a number I can calculate. This is a number I can calculate. This is a number I can calculate. Okay, so question is, what should those numbers satisfy so that no matter which hk I choose, I will always get something positive. Of course, I'm not going to choose hk equals 0, 0, then clearly it will be 0. Okay, other than that. So is it possible? So this question was first addressed by Gauss. Okay, so it's a very classical thing. So there are conditions on this. So I'll give one condition. Well, the condition is the same, but I'll give one easy derivation of the condition. It takes long. I'll just give you the main step, not even the main steps. Then you can fill in the details. Then the rest you can look up number theory books. So let me do this. So the question here is this following. What conditions should these numbers satisfy so that Q0 is always positive for any hk, which is of course different than 0, or I can ask the same question, Q0 negative for this, or Q0 changes sign. But here, changes, okay, let me leave it like this and explain this. I want Q0 to change sign, meaning that there are hk's, again the ratio is important, there are hk's for which this number will be strictly negative, and there are other hk's for which this number will be strictly positive. Okay? So that will tell me that around this point there are always nearby points which are larger than this, and also other nearby points which are smaller than this. So it's going to be a saddle point. Okay? So this will give me a local minimum. No, if Q is always negative, then this is large, so this gives me local maximum. Okay, so these will be the conditions. Okay, then x sub 0, y sub 0 is a local minimum. Okay, so here local maximum, and here saddle point. Okay, so you see what we are doing is relevant to our search for minima and maxima. Okay, so now let us go back to this problem. So what we do is, okay, now since we understand that we are calculating these at x sub 0, y sub 0, I'll stop writing x sub 0, y sub 0 because I'm getting tired. I'll just write f derivative. Okay. Now multiply both sides of this by, I think, fxx. Okay, so, well, it's written here, so I just take it from here. So I multiply both sides. Okay, it's understood that all evaluate at x sub 0, y sub 0, q evaluate at 0. Okay, so this is equal to, after rearrangement. So you see here I have square of this plus 2 times this. So this is begging to be completed to a square. In order to complete this to a square, I add the square of this. Since I added that, I subtract the square of this from here. Okay. So what happens is this. I have fxx times h plus fxy times k square. Okay, so I added the square of fxy times k. Okay, so then I have this square. Now I multiply this by fxx. Okay, so I have here I have f plus, here I have fxx, fyy. Okay. K square. Okay, so this is going to be multiplied by k square because I have this. And I also added here the square of this times k square, so that you see I obtained this. So I subtract that. fxy square and everything k square. Okay, so this is how this expression shows up. Okay, so now this is a famous expression. We call this d. Sometimes in the books it's called d. Okay, but traditionally it is denoted by this discriminant. Okay. Now, if you look at this thing, this part is a square. Okay, so it will never make this negative. So if the discriminant is positive, so now we can make some conclusions. If the discriminant is positive, you see this is positive, or well, this side is now sum of two positive things. Then this times this is going to be positive. It means that they are both going to have the same sign. So I also need to check the sign of this. If the sign of this is also positive, then this is positive. Okay, when I said this, remember, now notice that I didn't mention h and k. Okay, so I just looked at the signs of algebraic expressions. I have a square here plus something positive, I'm assuming, something positive times a square, so the right-hand side is positive. Okay, so therefore the left-hand side is positive. If the sign of this is positive, then this is positive for all possible h and k, except the trivial case when you put hk equals 0, then everybody knows you get 0. So we are not talking about that. Okay, so that's one condition. If the discriminant is positive, but the sign of fxx is negative, then q must be negative. Okay, then we are in this case. Okay. If the discriminant is negative, then you cannot say. Then you can check that by arranging h and k. You can change the sign of the left-hand side. Okay, so then we are in the last part. If the discriminant is 0, then you see that you can play with this thing and you can make this 0. Okay, when q of 0 is 0, when q of 0, why are we obsessed with Q of 0 because the sign of Q of 0 would tell us the sign of QC at nearby points. If Q of 0 is 0, it doesn't tell us anything about the nearby points. Okay? So when the discriminant is 0, there is no way to predict the sign of Q of C. That was the whole thing was to, you see, we are all trying to find the sign of Q of C. Okay, so that's the second derivative test. So I'll just write the first condition and the rest you can follow from there. Okay, so suppose discriminant, remember that I'm calculating this discriminant at x sub 0, y sub 0 is positive, then fx, or rather let me go step by step since I'll do only one case, then right hand side is positive, so left hand side is positive, so fxx and q have the same sign, so this is, remember, 0, have the same sign. So it means that I need to check one more thing. If fxx is positive, then q0 is positive. But q0 is positive means that then qc is positive at nearby points, at nearby c. Okay? But then it means that, okay, so it is here, and it means that then x sub 0, y sub 0 is a local minimum because the value of the function at nearby points is always larger. That's why I'm getting positive here. Okay, so this is one case. Now, if this is positive and if this is negative, then this is negative, then it's a local minimum. And for when the discriminant is negative, again, you have to play with h and k, and you can show that you can change the sign arbitrarily. Well, arbitrarily means there are the directions where the sign changes. Okay, so this is going to be the conclusion of the second derivative test, which I'll write in a minute. But just for cultural information, also look up number theory books. In number theory books, you will see that this RQ is going to be written like this in matrix notation. Okay, so here I have fxx, fxy. Here I again write fxy, fyy. And here I have hk. Okay, so with matrix notation, you see if you multiply these, you get a number. Then the condition is what should be invariance of this matrix B, so that this is always going to be positive. Okay, so this is always positive if determinant is positive. Check that the determinant is discriminant. So this, and one of these entries is positive. You see that since when this is positive, the sign of fxx and the sign of fyy must be the same. Okay? Otherwise, this cannot be positive because I'm subtracting something from this. If they have different signs, then this will be negative. This is negative. It can't be positive. So we are not obsessed with fxx. You can also put fyy here. And fxx positive, then q is positive. There is a technical name for this in number theory books. Such functions of h and k are called bilinear forms, quadratic forms. This condition is called being positive definite because it's never 0 and it's always positive except in the trivial case. And similarly, when it is negative definite, then the determinant must be 0, positive, and one of these must be negative. Well, choose this one negative. And when it changes sign in number theory, it's not called a saddle point, it's called indeterminate. Indeterminate means sometimes it's positive, sometimes it's negative, but it's never 0. Okay, so this is just for just magazine information. So you see, now we know why the second derivative test works, and in particular, why we can't say anything when the discriminant is 0. Okay, so otherwise, if you don't go through these things, I write down the second derivative test. It's just like magic. And then, of course, you forget sometimes why. There was some case in which you didn't say something, but what was the case? So, okay, let me write now the second derivative test. Okay, so, okay, so finally, the second derivative test. Okay, so we have a function f is a function of two variables having has continuous second partial derivatives. Okay, because we use this in the continuity argument, so we require this. We also use the fact that, well, where was it, that this thing is 0, so it means that this is a critical point. X sub 0, y sub 0. So actually this has continuous second partial derivatives around x sub 0, y sub 0, but we will be doing this globally, so just me write around x sub 0, y sub 0 in an open neighborhood of x sub 0 and y sub 0. X sub 0, y sub 0 is a critical point. Okay, so this means the first partial derivatives are 0 equals 0, and fy x sub 0, y sub 0 equals 0. Okay, so this means that the tangent plane at that point to the surface is horizontal. Okay. Okay, so this argument tells me that now we can say something. Okay, so let also discriminant of x sub 0, y sub 0 be fxx. So I write the discriminant here, minus fxy x sub 0, y sub 0 square. Okay. Now I think these are all the things that we said. Okay, then first, if discriminant is positive and fxx, okay, let me, since I'm going to write this once, let me evaluate these at the point. F evaluated at that point is positive and fxx evaluated there is positive, then x sub 0, y sub 0 is a local minimum point for f. Okay. 2, if discriminant is positive and fxx is negative, then this is a local maximum point. And what else did we say? If this is negative, I can change the, if discriminant is negative. You see, when it is negative, then I don't care about the sign of this because I can change these things. Then x sub 0, y sub 0 is a saddle point. And 4, well, actually we can stop here. Okay, so what happens when the discriminant is 0? Well, you can't use this. You see, it doesn't make any claims there. Okay, so but just to emphasize it, we sometimes include this. If discriminant x sub 0, y sub 0 equals 0, then you are on your own. Then this test does not say anything. Sometimes to make it sound scientific, we say the test is inconclusive. Since it's such a nice word, everybody thinks that the test has said something at that point, but it's just a polite way of saying that the test doesn't know what's happening there. Okay, so this is the second derivative test. Now let me write the procedure to solve such problems. Okay. So first we will look at functions defined on all of R to solve min-max problems for f, x, y defined on R2. So this is going to be our first type of problems. The second type will be restricting this. Instead of having R2 here, we'll restrict the function to a smaller set. How do we solve the problem there? We will use this, and of course, just like we do in one-dimensional case, you also check the endpoints. Here, the endpoints will be boundary points. You restrict the function to the boundary points in the plane. Boundary points will be curves. So when you restrict it there, you will have a function of a single variable defined on an interval. So you'll find the critical points inside, and you'll again check the endpoints. Okay, but that's next week. So this week we have this. Okay, so first solve for critical points. So you want to solve this equals 0 and this equals 0 simultaneously. Okay, so this is the tough part. Solving two equations, two nonlinear equations in two unknowns. Okay, there is no method, no well-known method for this. It's complicated. So in the exercise, you will see that f is generally a quadratic polynomial. So when you take the derivatives, you get linear equations. So you have two linear equations in two unknowns, you immediately solve this. If f is a cubic polynomial, then it is so cooked up that when you look at them, some roots are obvious, so you can always factorize something out. Okay? So given a general polynomial, you cannot solve this. So if you are doing this by hand, the examples given to you will be simple. But in real life, this is the bottleneck. So this is where you have to use either your creativity or some software. Okay, so this is the complicated part. So that's the so-called bottleneck. Okay, so if things can pass through here, the rest is easy. Okay, so suppose you found the critical points. So suppose now you found, so this is the first step. Second, suppose you found the critical points. Okay, so say x sub 0, y sub 0 is one of them. Now you have to decide these things separately. Okay, apply the second derivative test if discriminant at that point is different than 0. Okay, now if you are lucky, it will be finished here. So I'll have 2 prime. If discriminant at this point is equal to 0, then you are on your own. Then anything goes. Then, okay, find by yourself the nature of x sub 0, y sub 0. Okay, so this is another this is another part. Okay, so here this is another part. You have to be using your brain and a lot of luck. Okay, anything goes. There's no method for this. You just stare at the function f. Okay, you stare at this function, you stare at this point, and then the rest is up to you. There is for every function and for every point, you have to do something else. But what you will do, nobody knows. You have to work. You have to try lots of things, and eventually, if you are lucky, you'll find the nature of this. Okay, without luck, nothing happens. Okay, so luck is necessary. Luck is not sufficient, but it is necessary. Okay, so next, after this, the problem is not finished here. Check if f is bounded or not. Okay, so that is limits of f as x and y go to plus or minus infinities. Okay. So for example, if the function is bounded, it doesn't go to infinity, plus infinity or minus infinity, and you found two critical points. At one point, the function has local minimum. At the other one, the function has local maximum. Then they are global mean and global max. Okay. Global mean and global max in the book is sometimes denoted as absolute mean and absolute max. The definition of this is not local, but the value of the function there is larger than the value of the. Now, tell if the critical point is local mean max, saddle point, or absolute mean max. Okay, so the whole idea is this last part. So let me note it like this. We start with this f of x defined on here, and we want to end up with this thing. Okay, so next hour now we'll give a break, and next hour I'll do examples. Okay, so that's the question. Given f, x, y defined on R2, find all its local mean, local max, global mean, global max if they exist. Tell us if they don't exist. Tell us if there are saddle points. Okay, so that's the problem. Okay, so you better like such problems because that's why you chose to be engineers and scientists. Otherwise, if you didn't like such problems, you would be in a different department. So next hour we'll have fun on trying to go from there to here.